Those of you at the back, can you hear me? Okay, everyone hear me, right? Okay, so I want to welcome you to another statistical machine learning class. Of course, I want to believe you've all seen your grade. Um, I think some are still being finalized, or those that didn't write in person, they're still being finalized. So, her grade will be released today. So, I think at this point in time, this is going forward, you have to take our things seriously because we're counting down to the final exam. So if I were you, attendance is very, very crucial. Okay, it's very, very crucial. Okay, so I want to welcome you to the covariance analysis. Let me tell you this: in statistics and statistical machine learning in general, um, analysis of covariance is very, very crucial. This is a new topic. Without covariance, there's no way I'll be able to see how variables move together or how they move apart. And covariance serves as an input for correlation. Without covariance, we may not be able to get a correlation. Without correlation, then it means we're not able to get relationship between variables. And that's why uh, in this topic, we want to focus on covariance analysis. Covariance analysis as it applies to portfolio theory. We actually want to go into finance. We assume that uh, there are different assets. Assets are random variable. Assets are random variable because different returns. Returns varies. Return from asset varies. And with the covariance analysis, I'll be able to see how return from assets, how they move together or how they move apart. So, and that is what we call portfolio theory. So in portfolio theory, we make use of covariance analysis because the idea behind this is can we have an investor want to maximize his return, okay, and also want to minimize the risk. So it's doing two things at the same time. Maximizing expected returns and minimizing the risk. Because of course there's going to be risk associated with return. But we're talking about maximizing expected return. We're going to be talking about mean. We know the idea of mean will be used. And if you're talking about the risk associated, then we need covariance. And the reason why we need covariance is because the risk associated may not be only attributed to risk for individual assets, but it can also depend on, the risk, the covariance, of returns. So because of that, we want to, in the outline, we'll be focusing on mean variance portfolio theory, then the covariance and correlation. Like I said, what we study is covariance analysis. The covariance analysis is very, very crucial in portfolio theory. Okay, so let's get started. Before first, I want to walk you through the mean variance. I just wanted to take a look at this. Okay, if you take a look at this, suppose we have a collection of assets. Okay, some investors have different assets they invest in. Okay, and we want to form a portfolio by determining how much to invest in each of the assets. let me tell you this. Investors don't just invest in an asset. They, through portfolio theory, will be able to optimally determine, what to invest, the amount to invest in a particular asset. That's what we call portfolio theory. Okay? So how much do we invest in each asset, for us to actualize our goal? The goal of an investor is to actualize, to maximize expected return and then to minimize the risk. Okay? Now, if you take a look at this, that very decision will be based on the mean and the variance of the portfolio. So mean and variance, very crucial. The mean is going to talk about the expected return, while the variance will capture the risk. Okay, if I want to have a measure of risk, I need the variance. Okay? Okay, now, if you take a look at what I said in the bullet here, I said, for instance, forming a portfolio, we want to form a portfolio that minimizes the variance of the portfolio return for a given expected return. For a given expected return, okay, I already know my expected return. Okay, now I actually want to minimize variance associated with that. Minimizing variance is minimizing risk. Okay, minimizing variance is minimizing risk. Now, to minimize the variance, we need to know what constitutes the variance. The variance of the portfolio depend, okay, not only on the variance of each asset, but also depend on the correlation between them. Okay, so this is similar to what you did in 5101, or in the theory of statistics, where the variance of x1 plus x2, when you have a variance of x1 plus x2, okay, let me write it down. If you have a variance of x1 plus x2, if x1 is an asset and x2 is an asset, then here, based on what you've done before, this is going to be variance of x1 plus variance of x2, right, plus 2 covariance x1 and x2. So what you see now is that the variance of the combination of assets depends on the variance of each asset and the relationship the asset has. Okay, now the approach, okay, to investing is actually what we call the mean variance portfolio theory, or we call them Markowitz. That was developed by Markowitz. Okay, Markowitz developed that very theory. Okay, so I just wanted to, and let me tell you this, and I said something here. I said to begin, we introduce some mathematical background on the code. Now, before we can dazzle into portfolio theory, before we can dazzle into application, I think it's better we have a recap first on the background of covariance and correlation in statistics, because without you understanding or you reflecting on that, there's going to be an issue moving forward, because we want to apply this in portfolio theory, but because I know some of you, or maybe you've already forgotten what you learned in 5101, or some of you have done that for a long time, And that's why we now want to go back now, refresh your memory. I want to refresh your memory now before we now apply this in portfolio theory. Okay, now I want to welcome you to conventional, statistics now, where the concept of covariance, correlation will be discussed. Now let's take a look at this. I have x1 up to xn. Okay, they are random variable. In portfolio theory, they represent return from assets. Okay, you have different assets. It's like having n number of assets that an investor investing in. Okay, now if you take a look at this, that was what I just said. If SK denote the return of asset K, then S model the return of n asset jointly, taking into account any dependence. So if we have so many assets, we have to look at it in a multivariate case where we can actually model them jointly. Why are we model them jointly? Because they have relationship. We don't just do what we do. We got a reason why we do what we do. Now, because of this, I'm actually going to come here. Okay, you need your, like this. You've seen this before, but we need to have a recap on this so that you'll be able to reconnect to, what the portfolio theory. Now, this is the covariance formula. The covariance measures, tell us how variables actually move together, how they varies together. Okay? But covariance is not consistent because a situation where we have different scales, where variables are on different scales or on different units. If I'm working with a data on maybe mass, MASS, if I compute the covariance for kilogram, the value that I'm going to get will be different from when I convert the data from kilogram to gram and compute the covariance, I'm not going to get the same results. So covariance is not consistent when when you have different units. And that's why we need correlation. Correlation is unitless. Correlation is consistent. Correlation is a standardized covariance. That's why correlation in statistical analysis, correlation is used, most of the time, because correlation is consistent. If I change from one unit to the other, I'm still going to get the same correlation value. Okay, so correlation measures not only how variables, how they varies together, but with correlation, we can determine the strength of the relationship. You may not able to determine the strength of the relationship when it comes to covariance. Covariance only going to tell you direction, but not the strength. But correlation tell you both. And if you take a look at this, you are standardizing covariance to get correlation. What you have at the top, what you have at the numerator is covariance. This guy is covariance. Okay. Now, what you have in the bottom is what you are using to standardize covariance. What you have at the denominator is, you have this the square root of the product of the variances, which is more or less like the product of the standard deviation for each variable. Okay. Interpretation of covariance. interpretation of correlations. You need to be able to know how we interpret this in case you're applying this in portfolio theory. Okay? Now, correlation is between -1 and 1. Don't forget, why covariance is a measure of linear relationship. Covariance is not a standardized measure. Please pay attention to that. But correlation is a standardized measure that will restrict the range of values you're actually going to get between -1 and 1. Okay? Now we have a way to interpret when the correlation is -1, when the correlation is 1, when the correlation is 0, when the correlation lies between -1 and 1. Okay? So you can see that, you can revisit that. Okay? And let me tell you this. When returns from assets are correlated, that is dangerous. I'm going to say that again. When returns on different assets correlate, that is dangerous. Because it means they move together. It means what happened to this asset happened to the other asset. Which means when you lose on this asset, you're going to lose on this asset. That's what it means. Okay? So correlation is not good for diversification of assets. I'm still coming to that. But what we're reviewing right now, we're trying to review, the underlying statistical theory that guide the explanation of covariance and correlation. And let me tell you this. When covariance equal to 0, correlation equal to 0. But converse is not true in general. Okay? When covariance equal to 0, because you want to determine the correlation from covariance. So the moment the covariance equal to 0, the correlation also equal to 0. Okay. Basic statistical properties of covariance. Why are we revisiting this? Because they're actually going to take a center stage when it comes to portfolio theory. Okay? Now, if I have X, Y, and Z, X, Y, and Z may be 3 different assets that an investor is investing on. Okay? Now, we believe that we have constants, A and B, that are actually Lysin ring number. Now, what are the properties of covariance? Okay? Because for you to be able to take a very good decision that that you are not going to regret, I'm going to say that again. For you not to mislead. Okay? For you not to mislead, you need to be able to understand the properties of covariance. Now, if you take a look at what I'm trying to say here, okay, the covariance between S and Y is the same as the covariance between Y and S. Okay? It's commutative. That's what I mean. Okay? Now, if I have a constant, let's pay attention. If I have a constant and a variable, a constant doesn't change. The covariance becomes 0. A is a constant here. S is the variable. Okay? A situation where I'm talking about covariance between X and X, the same variable, then automatically I'm talking about variance. Covariance of X and S is the variance of X. Covariance of Y and Y is the variance of Y. I just wanted to take note of that. In another property, take a look at this guy here. At times we can have a covariance between a linear combination and a variable. A variable is Z, okay? But you want to look into the relationship between a linear combination of X and Y and a variable Z. Linear combination, because this guy here, AX plus BY, that can give another variable N. So this is like, I'm actually talking about the covariance between M and Z, where M is a linear combination of X and Y. Okay? Now, this is how we can express that. That would be A covariance SZ plus B covariance YZ. You're actually going to bring out the constants. Okay, A and B. That's exactly what you're doing now. Now, take a look at this guy. I think I wrote this guy before. The variance of the addition of X and Y, okay? The variance of addition of X and Y is going to be equal to the sum of the individual variance plus 2 covariance. Okay? This is very, very crucial in portfolio theory. If I now want to generalize this, please pay attention, from S and Y to maybe X1, S2, S3, and so on like that, I'm actually going to have this guy. Okay? I'm actually going to have that guy. Okay? Which means the variance of A transpose S is going to be equal to the variance of that. Okay? And that is going to give us this. Okay? So now, let me now go. Let's talk about sample now. Because if I'm going to do research, I'm actually going to work with sample of data. Okay? So if I have X variables, Y variables, okay, I can find the mean of X. Okay? I can find the variance of X. I can find the sample covariance. The moment I get a sample covariance, then I'm actually going to get sample correlation. This is for situation where I only have X and Y. Okay? X and Y. I'm going to have the mean for them. I'm going to have the variance for them. I'm going to have the sample covariance. Then I'm also going to have the correlation. Take a look at that. Okay? Now, if you take a look at what I'm having now, okay, this is sample covariance and sample correlation. The two of them are not the same. The sample correlation is derived from sample covariance. Okay? You can see what I have now. Sample correlation. In the sample correlation, the numerator is the covariance. The denominator is the product of the standard deviation of S and standard deviation of Y. Whenever you divide a term by standard deviation, you are standardizing. That's the way we standardize. Okay? Let's take a look at that. Okay. Now, if I now want to generalize, I have so many variables now. The same way I'm actually going to have so many assets that I'm investing in. X1 up to Xn. Okay? But because we live in a stochastic environment, we live in a probability space, okay? A measure of risk we have to do with the covariance structure. So if I have an X, then I'm also going to have the covariance S is going to be that. Where the element in the diagonal, there will be variances. Variance of X1, variance of X2, until we get to the variance of Xn. In the half diagonal, you're going to have opportunity to see the covariance between any pairs of the variable. So the covariance matrix, the covariance structure, very crucial in portfolio theory. Okay, can we have a way to characterize a covariance matrix? Okay. Now, I said here, please pay attention. Given a matrix, it is useful to know whether it is a valid covariance matrix. So how do I know if a covariance matrix is a valid one? And this is what our investigation. Because invalid covariance will actually mislead us when it comes to investigating the risk associated with portfolio. Okay. Now, it means we need to investigate this mathematically. We have a mathematical way of investigating how valid is a covariance matrix. We don't just do what we do. We got a reason why we do what we do. So what I'm trying to showcase right now, how can we trust our covariance? To trust our covariance, it has to be valid. How can we investigate the validity? And I needed to pay attention. We have a mathematical properties. Covariance must actually follow, okay, before we can say the covariance is valid. Number one, please pay attention. Number one, it has to be symmetric. The covariance matrix we're talking about is always going to be a square matrix, where the numbers of rows and the numbers of columns are going to be the same. And when I find the transpose of a covariance matrix, it should give itself. It should give the same as the original. That is one of the ways to validate a covariance matrix. Does that make sense to everyone? That is what we call symmetric. Okay. Now we have other properties of covariance that I actually want to discuss right now. Okay. Now another property is that there should be a covariance should be positive semi-definite. You know what I mean by positive semi-definite? In the diagonal, there shouldn't be negative. I can have 0, that's no problem. Okay, I can have 0 or greater than 0. That's what we mean by positive semi-definite. When I say positive definite, when I remove the semi, then all the values in the diagonal has to be greater than 0. That's a strict one. But we don't require that strict one. Positive semi-definite is enough. Okay? And let me also tell you this. That covariance, like I said, is symmetric and it must satisfy that quadratic form greater or equal to 0. The quadratic form is when you have A transpose multiply the covariance under investigation multiplied by A. A is a constant matrix. And that should be greater or equal to 0. That's a quadratic form. Okay. And of course, it must satisfy all of that. So what I'm trying to showcase right now, because covariance matrix is very, very essential when it comes to investigating risk in portfolio theory, then we need to ensure that mathematical properties of covariance actually hold. We don't want to work with invalid covariance. If you work with invalid covariance, you're actually going to mislead. Okay. Now, this is the review of the covariance property. I want to go back to financial, asset returns now. I also want to have before we go into portfolio theory, okay, you know what I just done? I just review covariance, property, because we're actually going to be using that in portfolio theory. But what I want to do now, because in portfolio theory, we're going to be focusing on returns. And we also need to understand what we mean by returns. Okay. We're going to be focusing on asset returns. Okay. We want to see what is the formula for asset returns. Okay. In terms of price. Please pay attention. We want to build up now. Okay. Asset returns. Let me tell you this. Every human being expects returns. When you invest in something, whether you invest in an academic, okay, or you invest by reading, by studying, every human being has expectation. Okay. Now, when you invest, okay, when you put money down on different assets, you're expecting something in return. So we want to talk about asset returns right now. And I need you to pay attention now. Now, look at this. Everything is going to start with price. PT, price at time T. Okay? So the price at time T, because the original price that we have may be complicated. For simplicity, we make use of the logarithmic one. When you take the log, when you have a big value, right? When you take the log of a big value, what happens is it becomes smaller, right? Okay, so here we let PT to be logarithm of a capital T, which we call the logarithm return or continuously compounded return on an asset. Okay, so now that is defined as what I have here. If this is the price, this guy is trying to say, the price I'm considering is a logarithm, is the one on a logarithmic scale. I'm not considering the original, the actual one, because that could be messy. Okay, mathematically, speaking, I want to work with the simpler one. Then I take the log of that. Okay, which is going to become this PT. Okay, but how do I get return now? RT, return at time T, is the logarithm of the ratio, at time of the price at time T to the price at T minus 1. When I say T minus 1, that depends. The T is your time. It may be month, it may be week. So I'm talking about the changes, that occur between the previous point in time and the current. The current is the price at time T. The previous one will be at T minus 1. And, when you find the logarithm of a ratio, the logarithm of a ratio will actually lead us to the difference, right? To the difference. Okay, so this is going to be PT, because if you take a look at what I have here now, please pay attention. This guy now, if I want to write that, it's going to be log PT, right, minus log PT minus 1, right? But because I said, let this guy represent that, okay, if small PT represent this one, then what is going to represent this guy is going to be this guy here. Can you see that? Okay, we're breaking things down now. Now, from there, okay, by Taylor expansion, okay, if the variation is relatively small between two time points, we're considering two time points, the current time and the previous, which we call the lag in time series analysis. Has anybody offered a time series analysis before here? Time series. Okay. Now, this guy, okay, we can rewrite it as this. Okay, using the idea of a Taylor expansion. which is going to be the logarithm into 1 plus RT. But let me tell you this, logarithm of 1 plus RT can be approximately called RT if you use the idea of Taylor series expansion in mathematics. Now, if you take a look at this, we normally want to use logarithm, when something is multiplicative and it's complicated, taking the log will return that to be additive, right? Log of a product. Log of ABC equal to the log A plus log B plus log C. Now, if I want to talk about multi-period returns, not just a single return. So the additivity of multi-period return will give me a k-period log return, which is it's going to be sum of simple single log returns, which is exactly what you're seeing here. Okay, are you having a k? You're talking about for a particular period, k period. And that is exactly, which is actually giving you the sum, sum of the logarithm, sum of k single period logarithm returns. Okay. You know what we're doing now? We actually, trying to review the background application. Okay, returns. We need want to understand the formula, for returns. Now, we have because we're going to be focusing on asset returns. Okay, we have what we call SS returns. Please pay attention. SS, when I say something is SS, then that means you have find a difference between something. That's why it's SS, right? So you see RT and that. This guy, some common reference assets. Maybe you are actually comparing a particular return with a reference one. Okay, that's why you're subtracting. You have two different return. And this guy, the one we normally use as a reference, is a return without a risk, like a baseline. This guy, RT, this guy is a risky. It's like you are comparing risky return with riskless return. The riskless return, an example of that, riskless assets, an example of that is the short-time United States Treasury bill. Okay, it's a riskless one. Okay, now, and I said, sometimes using SS returns might make the problem statistically easier. We actually want to apply the knowledge of statistics here now. We don't just want to use any form of return, but the return that will make the process statistically easier. We don't want the one that will complicate the method that we want to use in statistics, otherwise we're never going to have a meaningful result. And that's why I said sometimes using SS return might make the problem statistically easier and could also make your process more stable. And that's why we may consider that. And I say this is because such a differential step may automatically help you remove some of the market variation or trend. Because here, this is like you are removing something, you are removing a baseline that in a way that is actually going to attain a very important property in time series analysis that will cause stationarity. Has anybody heard about stationarity? The stationarity is that assumption is that the price or as the return should be stable. Let me tell you something. In life, I don't know if things have been stable, we are never going to be worried. We only get worried when things change every day. That's why we get worried. Okay. Now, and I said here, please pay attention. I said, The method that we introduced today will be applicable if you replace the return by excess returns. Why excess returns? Stability, and not only that, it will make your method, the statistical approach, more easier for application. Okay, and for simplicity. Okay, now I'm moving now. Moving now. Now, we now understand what to use. We've reviewed the statistical background of covariance and correlation. We've looked into the properties of correlation, of covariance. We've also looked into the returns. We've actually seen the one that we actually are going to use that will make our method of statistics easier. Now, let's return to portfolio returns. We want to go into portfolio returns now. Why is it called a portfolio? Because it's going to give us a combination of assets with the weight. The weight of each asset is the one that we want to decide on. The weight is going to be the amount an investor is going to spend on each asset. They don't just spend money on a particular asset. Okay. Now, I'm actually, if you take a look at that, also I said WI will be the weight of the asset. Okay. And that will be expressed in percentage. Okay. Now we're going to have this. Okay. WI PT. Okay. Now, that is actually what we're going to have. Okay. Now, in the hand, we actually are going to have this. Let me quickly move here. Okay. Now, because what I'm interested in, what would be the overall return from the portfolio? The portfolio, let me tell you this. If a portfolio is a random variable, okay, that RT is a random variable, but the portfolio itself consists of several random variables, several assets that has a weight. That's like a linear combination. Like I'm going to have, the portfolio is going to be R1, W1, R2, W2, R3, and so on like that. Okay, and at the end of the day, I'm actually going to have RT equal to summation WI where RT now is now going to be the net return for the entire portfolio. And of course, in a log, using the logarithmic one, okay, is what you have here. Take a look at that. So eventually, that's what you have. Now, if that is what I have, okay, now I have this guy now, okay, because this is the portfolio that we're talking about. The portfolio is a random variable. The portfolio is a random variable. Don't forget the 5101. If X is a random variable, the function of S is also a random variable. So if each asset is a random variable, the linear combination of the asset also going to be a random variable. Then I can, oh my God, I can now find the mean. I can find the expected value of R, which is going to be the expected value of a linear combination of assets. Then I can also find the variance. Look at that. Okay. The mean, the expected value of R is actually going to be the mean of return. Okay. The mean of the portfolio. While the variance of the portfolio will actually is a measure of risk. Okay. So I just wanted to take note of that. Oh my God. I'm going to have a covariance matrix. Okay. For R1 up to RP, don't forget. Then if you take a look at this, weight must be at least, it has to be greater or equal to 0. It's either I put money in one asset, okay, or I don't put money. Does that make sense? Then the sum of the weight has to be equal to 1, which means I spend 100% of what I want to spend on all the assets. Okay, but we can also have situation. I'm going to walk you through situation where the summation of the weight can be greater than 1. That's something that we call short selling. But I'm still coming back to that. But right now, I'm dealing with the conventional one. Okay, now my co-weight portfolio theory. Okay, I said the first concept portfolio study is risk. If you want to, whatever we do in a stochastic environment is very risky. But someone who is not ready to take a risk, according to a philosopher, may not. Oh, okay. Look at what happened, where some astronauts, I don't know whether you heard the news, they traveled to the moon. They actually took a risk. But, at the end of the day, that will lead to discoveries. Good for the world. They took the risk. And at the end of the day, it's something that will worth celebration because that will lead to more discovery. Okay. Now, if you take a look at what I have here, we want to talk about an investor really want to minimize the risk and also want to maximize expected return. But there's no free lunch. There's no free lunch. I just wanted to take note of that. But what my core portfolio theory is going to say, okay, for a given expected return, please pay attention. For a given expected return, okay, I want to minimize risk. For a given risk, I want to maximize return. That is what. So the rule of thumb, so what we need to do is we should diversify. Investors should diversify. Diversification is mix assets that are risky with the ones that are not risky. Does that make sense? Don't just invest on so many risk assets. Mix them together. So the rule of thumb, diversification via a portfolio tends to reduce the risk of risky investments. Okay. Now, how am I going to know whether that happened? Then, if the conventional variance is less or equal to that, and that less or equal to that, okay. And I said to reduce risk through diversification, an investor usually has to settle for lower expected return than those of the riskier asset with high mean returns. This is what happens. If you want on a normal ground, if I want high mean return is associated with high risk. Low mean return is associated with low risk. We need to find a way in the middle. So how can we find a way in the middle? And that is what Markowitz, and that is what we're going to do in the next lecture, where we're going to see the principle used by Markowitz in ensuring that, in determining the amount of money to be invested, which we call the weight, to be invested in each asset. I'm actually going to show you, I'm going to consider, okay, when I have two risky assets, what happen? When I have a risky asset and a risk-free asset, what happen? And so on like that. And you're also going to see the benefit of diversification. That is what I got for you today. Before I go for 1 minute, you've seen results, okay, for midterm 2. If I were you, you have to pay attention to whatever we're doing now. The final has a very huge weight, okay? If somebody is going to have A in this course, you have to have A in the final because it has a huge weight, okay? What's going to be my joy at the end of the day is if everyone in this class has A, that would be my joy, okay? But you got to work for it, okay? Take the risk, okay? And at the end of the day, you're going to see maximum expected return. Okay, bye for now, everyone.